Welcome to the online lecture series of Basics of Computer Network. We are starting unit number 1, that is data communication and network models. So let's start with today's lecture. Guys, last lecture we have studied about a digital transmission of signals, that is analog to digital conversion. In that we have seen ASK modulation, FSK modulation and PSK modulation. After that, we have seen the second method, that is digital conversion. It means over there we have studied line codes. That what are line codes? What are the characteristic of line codes? Then what is sampling, quantization, encoding? All these things we have seen in previous lecture. Today we are going to discuss about transmission impairment, Shannon Hartlay theorem and channel capacity. So let's start with transmission impairment. Now guys, when the signal it is going to travel or transmit through a transmission medium, those mediums are not perfect. So those imperfections it is going to cause the impairment. Impairment in the sense guys that whatever the signals at the front end and at the end of the transmission medium, they are not same. It means what the data we have transmitted, the data we have not received in that form. So that is nothing but your impairment. So basically impairment causes, it is of three types: attenuation, distortion and noise. Now what is attenuation? Whenever the signal it is going to travel through a transmission medium, it loses its energy. That is, loss of energy is nothing but your attenuation. So basically, as we know that all the transmission medium, it has its own resistance. So now in order to overcome the resistance of the medium, the signal has to lose its energy in the form of heat. So you may have experienced when the electrical signals are carried through any wire, that wire get warm, little bit hotter, due to what? Loss of energy in the form of your heat. So in the figure, you can see that one. In order to compensate this loss, we have introduced an amplifier over here. You can see this, there are 3 points, point 1, point 2 and point 3. So when the signal, original signal, it is being transmitted, you can see while reaching to point 2, it is get attenuated due to the loss of energy in order to overcome the resistance of this transmission medium. Now in order to overcome this loss, we need a compensation, and which is achieved by using this amplifier. Then this amplifier again, it is going to amplify your attenuated signal and it can reach to its destination. Next guys, decibel. So basically guys, whenever we talk about a signal either lose its strength or gain its strength. So the engineers, we the engineers use one, one term that is called a decibel. So decibel, it is the unit which is going to measure the relative strength of the two signals or one signal at two different points. And remember this decibel, it is denoted by this dB. And decibel, it could be negative if a signal is attenuated, and it is positive if a signal is amplified. And this decibel, it is given by the formula, that is dB is equal to 10 log of P2 by P1 to the base 10. So P, it is nothing but your power of the signals. So P1, it is a power of a signal at a point 1 and P2, it is a power of a signal at a point 2. But in some books, you can see it in terms of voltage also. We have expressed the decibel in terms of power signal. But if we are going to express in the form of voltage, as we know, power, it is related with the square of the voltage. So we can write it dP is equal to 20 log of V2 by V1 to the base 10, 20. because it is a square of voltage. Power, it is nothing but your square of voltage. That's why. But over here we have expressed in terms of power only. So that's why the formula it is 10 log of P2 by P1. Now, suppose a signal, it is traveling through a transmission medium and its power it is reduced to 1/2. That means P2 is equal to what? P1 upon 2, right? So in this case, the attenuation, the loss of power, since power it is reduced, it means attenuation it has been taken place. Attenuation taken place in the sense what? Loss of power. So how the loss of power it could be calculated? See now, as we know the formula that 10 log of P2 by P1 to the base 10. So what is P1? It is already given, P1 over here. And what is P2? P2 is nothing but your 1 by 2 P1, that is a 0.5 P1. So P1, P1 get cancelled. What remain? 10 log of 0.5. And log of 0.5 to the base 10, it is minus 0.3. And 10 into minus 0.3, it is nothing but your minus 3 dB. Unit is dB. Now guys, we also use this unit decibel because the decibel numbers, it can be added or it can be subtracted. Because it is not the case that signal it is going to transmit between 2 points only. There could be a many different points are there. You can see the signal it is going to travel from point 1 to point 4 through point 2 and point 3. So it may happen some through for a particular section, for a particular transmission medium, there could be loss, or in between there could be amplifier, the gain it is there, then again attenuation it is there. So what we can do it, we can find the resultant dB, because we can do the cascading of it. The numbers, the decibel numbers, it could be added or subtracted. So as you know, the point 1 to point 2, the attenuation it is a minus 3 dB. And at point 2, the amplifier we use, so it amplifies by 7 dB. And again, when it is going to travel from point 3 to point 4, it has a loss of minus 3 dB. So you can calculate it just by minus 3 plus 7 minus 3. What is get? Plus 1. So the resultant decibel, resultant dB, it is what? 1 dB. Understood guys? Now, second impairment, it is your distortion. Distortion means the signal when changes its form, changes its shape. So each signal component, basically guys, what is going to be happen? A composite signal, it consists of different signals of different frequencies. And each those signals, they having its own propagation speed. So due to which what is going to be happen, all those signals, they are going to be arrive at the destination. They may have their own delay, different delay, because composite signal, it consists of different signals, right? So due to this differences in the delay of those different sine waves, different frequency components, they may cause a difference in the phase. That's why they are going to change the shape. So you can see it over here. At the sender, the composite signal, it consists of 3 sine waves, see. And at the transmitter, they are in phase. They are going to start at the origin. It consists of 3 sine waves. Together, it makes this composite signal. But when it is transmitted, since this composite signal, it consists of a simple sine waves, so they may have their own propagation speed. So you can see it how they are out of phase now. This is a first harmonic, then this is a second. See, it is starting at the 90 degree, then 180 degree. So there is a variation in their phase, variation in their propagation speed, which results in the distortion in the shape, in the form of your composite signal, which is being received. So you can see it, the shape, it is little bit distorted. So hope so you understood this concept. Now, noise, it is another problem, guys. Then there are several types of noise are there, such as thermal noise, induced noise, crosstalk, impulse noise. These all noise, they are going to corrupt the signal. Thermal noise, in the sense what? It is a random motion of electrons, which is going to create some extra energy, extra signal, which is not the original one that we have transmitted it. So due to the random motion of electrons, it is going to give rise to a extra energy, extra signal. Induced noise, basically this noise, it is going to induce due to some electrical appliances, as your motor, some appliances are there, radios are there, welding machines are there, any could be, which is operated on this electricity. So out of this, what is going to be happen? These appliances, which induces noise, they act as what? Transmitter. And your transmission medium, they acts as a receiving antenna. And so similarly, another, it is your crosstalk. Crosstalk in the sense what? That addition of your signal into your original wire by some another wire. If two wires are there, they are going to parallel to each other. That may happen, the signal present at medium 1, it get interfere, it get added to the signal which is traveling through wire 2. So this crosstalk, it can be removed or it could be overcome, reduced by twisting the pair. That's why you have observed that we have used a twisted pair cable. Why we are going to twist it? In order to nullify the effect of this crosstalk. And next, it is your last, it is your impulse noise. Impulse means spike. Spike at a particular instant. And after that instant, it gets normalized. And this impulse noise, this sudden spike, it may come due to, lightning, right? And so all these are the sources of noise which is going to corrupt the signal. So you can see it. This is your transmitted signal. And in that transmission medium, while transmitting it, the noise, it has been added to it. And this is your received signal. So we have to take care about this impairments. Now, signal to noise ratio. So, in order to find the theoretical bit rate limit, we are going to use the term that is signal to noise ratio. It means it is a ratio of the average signal power, which is denoted by S, to the average noise power denoted by N. Because when the signal it is going to transmit, it has its power, that is S. But in that signal, the noise, it is being added, and noise also, it has some power, that is N. So S upon N, it is nothing but your signal to noise ratio. And signal to noise ratio, when it is expressed in dB, it would be given as 10 log of SNR to the base 10. Understood? And remember, ideally the signal to noise ratio, it be infinity. Practically not possible. It should be high, as much high possible. So if SNR value is high, in the sense what? Signal power is very high. And the noise power, it is can't affect your signal power. So that's why it should be always high. Now take this one example. The power of a signal is 10 milliwatt. As we know, the power, it is expressed in watt. So 10 milliwatt, and the power of the noise is 1 microwatt. So what are the values of SNR? Simple. That SNR, it is given by what? Average signal power upon noise power, that is a 10,000 microwatt upon 1 milliwatt. So it is 1 microwatt. You can write it 10 milliwatt as a 10,000 microwatt. It is one and same. and over it is a 1 microwatt. So microwatt get cancel. What remain? It is a 10,000. So SNR it is what? 10,000. Signal to noise ratio is 10,000. But if you want to make it to convert into dB, then you can use it 10 log of SNR, that is 40. 10 raised to 4. So the SNR in dB it is what? 40. Now you can see what I told. If the larger value of SNR it is there, see, it means the signal power it is much more as compared to the noise power. It is very much low. It means the noise it could not affect the signal as much that instant or extent. Sorry. So due to which you can observe the shape of that signal. It is almost square. Just the top it has been disturbed or distorted. But if the value of SNR is very, very small, it means the signal power, it is less than that of a noise power, then noise, it can completely dominate your signal, and this is would be your received signal. So that's why SNR, it should always be high. Now, data rate limits, which is also called as bits rate. It means how fast we can send the data, how fast we can send the bits per second. It depends on the three factors, that is the bandwidth available, level of the signals we use, and the quality of the channel, that is a noise level. So it is not the case, guys, that whatever the bandwidth available to you, the bit rate would also be very high if the bandwidth is very high. I can explain this concept as like, suppose for a national highway, it has a bandwidth available that is of 10,000 cars per minute it can pass it. Next, it is your data rate limits. So how fast we can send the data, how fast we can send the bits per second, it depends on the three factors, that is the bandwidth available, level of the signals we use, and the quality of the channel, that is a noise level. Now, we are assuming a channel that is a transmission medium, it is a noiseless. So we are going to define the Nyquist bit rate, that is the number of bits transmitted per second, which is given by the formula that is 2 into bandwidth into log of L. Bandwidth, basically it is the bandwidth of your channel. L, it is going to tell you the number of signal levels which are going to represent the data. So it is easy that if I am going to increase the number of levels, then the bit rate it is going to increase. It is a general understanding of that one. But guys, it is not always the case, because if the level it is a 2, it means 0 and 1, signal levels are 2, that is a 0 and 1, then receiver it may easily understood these two levels. But if you are going to increase the L number of signal levels, suppose it is a 64, then the receiver may get confused. It may get, couldn't understand those individual each level is 64 level. So due to which it may happen, the reliability of the system, it may reduce. Now, next part, that is the Shannon Hartlay theorem. It is one of the most important theorem, guys. So please carefully understand it. Now, guys, in information theory, the Shannon Hartlay theorem tells the maximum rate at which the information can be transmitted over a communication channel of specified bandwidth in presence of noise. So basically, the Shannon Hartlay theorem states that the channel capacity C, meaning the theoretical tightest upper bound on the information rate of the data, that can be communicated at arbitrarily low error rate using an average received signal power, that is S, through an analog communication channel which is subject to wide additive Gaussian noise of power N. So this theorem basically it is going to describe that channel capacity for such a communication link, there is a bound on the maximum amount of error-free information per unit time that can be transmitted with the specified bandwidth in presence of noise interference. So assuming that the signal power is bounded and the Gaussian noise process is characterized by a known power or power spectral density. And this law, it is named after the Claude Shannon and Ralph Hartlay. So basically guys, in this we are going to consider the noisy channel, because ideally no channel it is a noiseless. In practical word, every channel it is a noisy channel. So Shannon it has determined the capacity of the channel. It means it is theoretical the maximum limit up to which the data it can be transmitted. Understood guys? So this is given by capacity C is equal to bandwidth into log of 1 plus SNR, or we can define it as a C, capacity denoted by C, into bandwidth of the channel log of 1 plus S upon N, that is signal to noise ratio, to the base 2. So this is the capacity, which is also, it is calculated in terms of bits per second. Now we would have now the example numerical on Nyquist bit rate and your Shannon capacity. Now guys, consider a noiseless channel with a bandwidth of 3000 Hz transmitting a signal with two signal levels, means 0 and 1. What could be the maximum bit rate? The maximum bit rate, it can be, you can calculate it as we know the formula 2 into bandwidth. Bandwidth is 3000 into log of L. L it is 2. So bit rate is equal to 2 into 3000 log of 2. So what is with log of 2 to the base 2? It is 1. So what is the answer? 6000 bits per second. Second example. Consider the same noiseless channel transmitting a signal with 4 signal levels, as like your 0, 0, 0, 1, 1, 0 and 1, 1. These are the 4 levels we got it. So the maximum bit rate, what you can get it, 2 into 3000 into log of 4, because over here L it is 4. So log of 4 to the base 2, it is what? 2. So 2 into 3000 into 2, it is at 12,000 bits per second you can transmit it for noiseless channel. This is the Nyquist bit rate. Now considering the examples of your Shannon capacity. Now consider an extremely noisy channel in which the value of the signal to noise ratio is almost 0. It means what? The noise is so strong that signal is faint. The actual signal, it is faint. So for this, the channel, the capacity is calculated as we know C is equal to B log of 1 plus SNR. And what is SNR? It is 0. And log of 1, it is 0. So what is the capacity of transmitting the bits per second? It is 0. Right? Similarly. Now we can calculate the theoretical highest bit rate of a regular telephone line. As we know, a regular telephone line, it has a bandwidth of 3000 Hz, that is ranging from 300 Hz to 3300 Hz. So the signal to noise ratio is usually what? 3162. Now we would calculate the capacity. So it is given by B log of 1 plus SNR. What is bandwidth? It is 3000 as given. And what is signal to noise ratio? 3162. So 3162 plus 1, it is a 3163. So what is the answer? That is 3000 into log of 3160, that is 11.62. That is 34860 bits per second. It is the highest bit rate of regular telephone line, that is 34.86 kbps, kilobits per second. Now guys, basically you can see from this formula for this Shannon capacity, that Shannon capacity, this formula, it is irrespective of your number of levels. Nyquist bitrate, it was telling you the number of levels. So in this, we are not going to consider the number of levels. It means whatever may be the number of levels are there, you could not increase the data rate beyond its capacity of the channel. But we have to consider the both the limits. The Shannon capacity, it gives you the upper limit of the capacity, and the Nyquist formula, it tells you how many signal levels we need. So we require both, guys. So if we have a channel with a 1 megahertz bandwidth, the SNR, the signal to noise ratio for this channel is what? 63. Then what is the appropriate bit rate and the signal level? So we can find it by using the Shannon formula, that capacity is equal to B, bandwidth into log of 1 plus SNR. As we know, bandwidth is 1 megahertz and log of 1 plus SNR, that is the 63. So guys, bandwidth is equal to 10 raised to 6, that is 1 megahertz, 1 into 10 raised to 6 log of 1 plus 63. 63, it is nothing but your signal to noise ratio. So 10 raised to 6 log of 64, so 6 Mbps, it is your capacity, that is the appropriate bit rate. And if you want to find for this what should be the signal level, then you have to use the Nyquist formula, that is twice of bandwidth into log of L. As we know, so it is going to give you the highest limit, that is a 6 Mbps. But for our case, we are going to consider 4 Mbps, a lower of 6 Mbps, because for better performance. So if we are going to consider bit rate 4 Mbps, that is equal to twice of bandwidth, that is a 1 megahertz into log of L. So L, we are getting it what? 4. The number of signal levels, it is a 4, because theoretically it is the capacity, it is a 6 Mbps. But for over this case, we have considered for better performance, we have considered the lower level of this one. So we consider 4 Mbps bitrate over here. So for the bitrate 4 Mbps, the signal of levels, it should be 4. Now guys, performance of the network, basically it is measured by means of the bandwidth. And bandwidth in two contexts, that is bandwidth in hertz and bandwidth in bits per second. So bandwidth in hertz, basically it is refers to the range of frequencies in a composite signal, or the range of frequency that a channel can pass. And similarly, bandwidth in bits per second refers to the speed of bit transmission in a channel or link. Next, it is your throughput. What is throughput? Measurement of how fast we can actually send the data through a network, that is your efficiency. Next, it is your latency. Latency means a delay. So it is going to tell how long it takes for an entire message to completely arrive at the destination from the time the first bit is sent out from the source. Because just by sending a first bit, we have to consider the entire message. The time it takes from the first bit which is being sent out from the source up till the last bit it has been received by at the destination. So this whole time, it is called a latency period, and which is given as propagation time plus transmission time plus queuing time plus processing delay. So propagation time, in the sense what? A time taken by a single bit, that is a distance upon propagation speed. So what is the time taken by a single bit? It is your propagation time. What is the transmission time? See, transmission time and propagation time, they are different. Propagation time, it is for a bit, single bit, but the transmission time, it is for the entire message. We can't send just a bit. We have to send the entire message. So how much time it taken by that message to be reached at the destination, the entire message. So that whole time, it is nothing but your transmission time. So definitely transmission time depends on the size of your message. So which is given by message size upon the bandwidth plus queuing time. Queuing time in the sense in between any nodes are there, any switches, hubs, routers are there. If they are busy or there is a congestion, then these packets, these beats have to wait for its time. Plus, so that queuing time plus processing delay. Processing delay in the sense what? When the packet it is arrived at the router, then router it has to process that packet. That where is the actual destination? What is the shortest path? Right? So through which node I have to send it? Which is the next hop? So all this processing delay, all the time required in order to calculate this, it is your processing delay. And last, it is your jitter. As I already told, it is a variation in the what? In the delay of the arrived packets that I already explained. That few packets, initial suppose one packet, it has a delay of 30 millisecond. In between two packets have a delay of 40 milliseconds. And last packet, it has a delay of 35 milliseconds. So the packets, they are going to arrive at the destination at a different time, which is not in proper order. That is nothing but your jitter. So guys, today we understood about transmission impairment. What is attenuation, distortion, noise? What are the types of noise? And then we seen the Shannon Hartlay theorem. What is the capacity of capacity of the channel? What is Nyquist bit rate? And we have solved few numericals on that one. So it's all about our today's lecture. And it is the assignment that you have to solve it. So please note down this assignment. The next module, that would be the last topic of the first unit, that is open system interconnect OSI model and TCP/IP whole networking. Basically it is based on this OSI and TCP/IP model, so it is one of the most important lecture. So this is my email address, you can note it down for any questions or feedback. So thank you very much guys for today's lecture.